Log on, tune in, find out. Another good idea from Cambridge.
To remain in the same spirit, we have designs for correlated observations. So Anatoly.
Thanks very much. Yeah, I put it on. I don't know how it works. Hello, everyone. My name is Anatoly Zhigljavsky. Control L. Yeah. All right. I'm going to build a reliable theory, asymptotic theory, by request. So my collaborators in this attempt will be Helga, Dete from Bochum, and Andrei Popelyshev, who supposedly is in Aachen, but nobody in Aachen knows him. I checked all other participants from Aachen. They never met him. And I'm not sure he's there because he changes places every so often that nobody can follow that route. So that's an example of chaotic behavior right now. Parts were done in collaboration with Cardiff people. It will be clear which parts. The generic model, the main model, no fancy business, just regression model with errors. The only fancy business is this correlation functions, rho t minus t prime. Very standard point, I don't know, problem discussed in many papers, I don't know. And I'll try to give some survey of what was done and why we were doing this. What did we do? Did we do anything? Or did anybody do anything useful here? That's kind of my discussion. So design is usually the set of points in our set T. And aim of design is to estimate parameters somehow. Functions f are known. Okay. Before doing that, we need to answer some questions. What is n? N is n capital is always number of experiments. Do we need n large or do we need n small? Do we need asymptotic theory anyway? If yes, then why? And there are all these famous examples when there are 4 points on an interval, and addition of fifth point only destroys the variance. So addition of points makes design worse. Okay, there are some fancy correlation functions and stuff, but the idea is there. So sometimes n equals 4 is better than n equals to infinity. Sometimes not. Sometimes large n is all right. So what happens if t interval? What happens if t is not interval? Difficult to say. It's difficult to say what happens when t is interval anyway, as we will discuss. But quite a lot of discussion can be extended to general sets, to cover everything Werner is doing, but quite a lot is not. So is the autocorrelation function known exactly or approximately? And that has some implications, because if it is not known exactly, just approximately, and using it exactly may destroy not only design but estimators as well. So related question, what kind of estimator we should use? I'll talk about that. So okay, what exactly is the model, etc., etc., etc. Okay, start with models. Simplest model is a mean. We just have mean plus stationary process. We will see that we can say something about this model. Not always, not for Werner purpose, which is fields and stuff, but sometimes we can say something. second most complicated model is the constant is replaced by function f of t. So it's just still one parameter model, but there is some function. It's actually a big step forward from first model to the second. Then enormous step forward to the third model, which is our generic model. And then there is step backwards with nonlinear models, because everybody linearizes and kind of. Model number 4 is I'm not going to talk about that because everybody knows. Model number 5 is non-parametric. It's all functional estimation, estimation of correlation process. Very difficult. Not going to talk about that. And model number 6 covers everything else basically. So it's everything possible. Lots of models already discussed in this conference. Not going to talk about that. I only will talk about number 1, number 2, and number 3. Okay. Two estimators, two candidates. So now consider only my generic model. So two possible estimators. Blue, which is in blue, which is also weighted LSC, which everybody knows, has some covariance matrix d theta hat, and standard LSC. Ignore correlations on the stage of construction of estimators. So is it good or bad to ignore? Okay, Gauss and Markov said no. They said that it's not very good to ignore. However, if we don't know correlation function exactly, that's one explanation why it might be safer to use second one. And second, there is a long discussion in literature about the difference between how much better is blue than least squares. And there is quite a lot of literature, and literature concentrates on the answer no. So literature concentrates on the answer that either asymptotically or just for some models it's the same thing. What I like this Grenander thing because the technique he used here, and then it was generalized by Noether and by some other people, to random fields. But it's still this model with a constant. It's basically a technique which I'm going to use here and extend. So it's all about maximization of some or minimization of some functionals. So the idea behind this is that least squares they just change probability measure, which is design, to sign measure, which is not designed, because weights they make a rule of assigning say negative masses to some points. That's all. So and if it happens, then solution of this when you write the variance, which is basically the same, which will be written below, is solution of the problem happens to be probability measure, then base linear estimator is the same as least squares estimator plus design is the same. So it's both pair design plus estimator plus design. Anyway, any discussion on this topic I accept very freely, but I'm not saying that LSC is better. For us, LSC is better for only one single reason. So come back. For us, this is all irrelevant. This is just trying to find any reason why we want to use this and not that. The only reason is that the first one is too difficult to analyze. It's just impossible, almost impossible to deal with. And the second one is much simpler. Now, get back to n infinity or non-infinity. Do we need this infinity or do we not? We don't need infinity. In practice, of course, we don't need infinity. It's not clear what infinity is anyway. And how much better designs with large number of observations than designs with small number of observations. All these examples I already mentioned. But if we want to solve the problem, there are several algorithms. The first one is direct minimization of the functional. Second one already cited. Somehow in the previous talk there was a reference 2004, but I had just printed before going to Cambridge paper, and it was 2010. I don't know which one is correct. It's probably yes. Maybe okay. Maybe I printed 3 printers. Okay, sorry. I thought it's 2010. All right. Anyway, there are lots of quite interesting discussion about how to construct designs. It's not only this Brimkulov. I don't know why Brimkulov. I think he was kind of PhD student. The main one was not Brimkulov. The main was Savanov. But as usual, third co-author has no references at all. Krug is a little bit known, but he didn't do anything. But it's all Savanov did, and not Brimkulov. So it wasn't much to do there anyway, because it's a very simple exchange type algorithm. But there are lots of intelligent discussions in some other papers, and in that book as well, of course. Especially the book of Noether. Is it good pronunciation? Noether. Noether. Okay. And some other papers. And there are lots of other papers. I did not print all of that. Again, that was proper estimator for improper estimator for LSE. You can do all the same, but simpler. Also, because there is equivalence theorem, you can do all these multiplicative algorithms. Of speeches, there is no Ben here because he would like that, and we did that in our computations. They can merge much faster, of course. Okay. Now, the main reason for sending n to infinity is the demand to build asymptotic theory. There is no big reason to otherwise. So some people try to build asymptotic theory to compare asymptotics. So maybe I'm wrong again. Maybe Henry will correct me. Where is Henry? But I don't really know any results of comparison n infinity and is not infinity, because it's very rarely when people really take these algorithms or whatever they can and try to see to check all this asymptotic theory and try to check whether these designs converge and stuff for non-trivial problems. So where is continuity in different sense, in the sense of n infinity? Okay, n infinity is kind of trivial, but in the sense of when correlation tends to in different asymptotics. Anyway, we follow the standard definition of design. The design points are quantiles of some function, which is inverse of CDF. That's the definition which everybody uses, starting probably with Sachs-Ilsenberger and forgot the name, Noether. Okay, the most famous by big margin are papers by Sachs and Ilsenberger. They considered weighted LSE, they considered some asymptotics, they considered limiting whatever optimal design. I'm not discussing that approach. I only discuss 3 issues related. First one, which doesn't contradict what you said before, that variances don't tend to 0 as n increases. They just tend to some final covariance matrix, which is optimal, or finite variance, which is optimal for scalar case. This is fine. Second remark is that optimal design only doesn't depend on correlation function. There is no correlation function there. There is a row of t comma s there because it's more general. They only depend on derivatives or even second derivatives, which first you have to know exactly, and second, because in a way there are too many points, far too many points in the interval. So what this asymptotic assumes is that you have this, I don't know, 0, well, it doesn't matter what interval you have, or if it is a space. There are far too many points inside. So there is no correlation, there is only derivative at 0. So basically all this discussion about correlation is not relevant. It's not really correlated observations, it's just how they are correlated when they're very, very close. And another note is that there is no connection to uncorrelated, to the main case of uncorrelated error. How would you make connection? You can't. So it's totally different. Now, from now on, I only consider simple least squares estimators, and my covariance matrix, I briefly come back to that one. So we have x transpose x minus 1, which will be our information matrix of design, usual information matrix. That's another m minus 1. And that is this weighted x transpose sigma x. So we see it here in this form. So when we go to the limit, consider just approximate design, any design, including endpoint design, arbitrary design. So then we have this expression. And this is what we will be dealing with from now on. M minus 1, this b, which is double integral m minus 1 again. Okay, so 3 cases, because I cannot go to this generic model because it's too difficult. So two simpler cases when we have just location scale model. We have variance, which is the first formula, just double integral of this rho u minus v dig psi dig psi. If we have function, we already have much more difficult. We have this denominator f square u psi du is our information matrix, but it's minus 1, and it arrives twice. Yes, and the general case. Okay, now we will always fight with the problem convexity, strict convexity, or no convexity, or what are the properties of our design optimality criterion, because then we will have to take, if we are not in the scalar case, we will have to take determinant or whatever we want to take and try to optimize. And there is no convexity in general. It's even worse. There is no convexity here in general. For some models, yes, but for few. There is, however, convexity in the original model, in the location model, in the location scale model. And the proof is based on Bochner-Hinchen theorem, because correlation function is positive definite. And it's basically one-to-one. You have Bochner-Hinchen, or Bochner, which was in previous talk. But I'm Russian. I always add Russian names to originally Russian, not really Russian, but always add some Russian name because just because. So the proof is similar. I mean, very simple. You just take the difference and see that the difference is this integral, where this is a sign measure, but because of this function is positive definite, this is okay. There is a problem with definition of what is positive definite. Are these matrices or integrals always larger than 0 or larger or equal than 0? This is a mistake. This is larger or equal than 0 in general, but but in this particular case, it's larger than 0. So it's strict convexity. Despite for positive definite function, you only need larger or equal than 0. There's some discontinuity between two notations of positive definite function and positive definite matrices. But in this particular case, it's fine. So this functional is positive definite. This matrix is positive definite, or just this is not a matrix, this is just a number. And therefore, criterion is strictly convex. And it's easy to prove optimality theorem for this particular model. It's again firstly proved by NATO. Okay, anyway. So we've done lots of exercises with different correlations functions. This is just to plot, just to show a nice picture. These are support points for some particular function depending on lambda. They're all discrete. The weights are, no, I forgot about the weights. Weights are not equal. The weights are some funny weights, but this is just support points. So just because it's a nice picture. But we had pictures for different correlation functions, and we wanted that to see convergence to the limiting design, which is in this and many other cases uniform, which is not first not big surprise, and second not very interesting. Okay. Already going to the second model is basically impossible here. Second model in this traditional case is okay. It's too difficult. I'll talk about that later. I'll come back to this. So the first model is simple, and lots of results can be generalized to more general, from interval to somewhere to fields somewhere. But already second model is too difficult in general. So directly because we don't have convexity. Okay. Now something different. There was Sachs, Illisecker, now Bickel-Herzberg. So what did they do? They considered least squares estimators, which leads to this matrix again, and then considered different asymptotic. They considered asymptotic when this is on the top. Rho n is rho of nt. So it's either they, when number of points arrive, their correlation function gets narrow and narrow, or the different interpretation, but the same thing is that interval gets expanded. So basically 1 point per unit interval. So instead of interval -1, 1, you become, say, minus n for n points. So kind of, okay, whether it's good or bad, I don't know. It's just different approach. What they achieved, they still have this m-1 and m-1 on the left and on the right, but instead of this difficult matrix with double integral, they've got single integral where the density comes in somehow, and then they were able to solve the problem, but only for simple particular cases as well. For location scale model and for the model. Okay, that's some asymptotic. Yeah, linear regression through the origin. So it's theta multiplied by x model. And then there are typical optimal designs look like that. That's from Bickel-Herzberg and Schilling. That's another paper, but the approach was Bickel-Herzberg, and they discussed quite a lot of analytics related to convexity. So this criterion in one parameter case, of course, because it's one parameter case, is convex. In two parameter case, it's already too difficult. So linear regression alpha plus beta x is already impossible case. They tried to solve that numerically and did some other things, but it's technically difficult case. So that's slide detour. What is nice about Bickel-Herzberg model is that it's possible to introduce, because in Bickel-Herzberg approach, the whole of correlation function is used. So, is it used well, or is it used wisely or unwisely? That's another discussion, but it's used. So, and there are some other correlation functions like long-range dependence, which with heavy tails. So we tried it, and it was fine. I gave a talk about 3 models ago about that. First talk, but it wasn't finished. Oh, 2 models. So with Nikolai, of course, because he's the main long-range dependence person, and he claims in the whole of Europe or something like that. Then similar, they're different. You cannot see the difference, but they're similar shape. Similar shape, optimal densities. That's analytic. So of course, you can do numerically quite a lot, but this is all analytic. Okay, but now different asymptotics. So Saxon will say many points in small interval. Bickel-Herzberg either few points in a long interval or the same correlation functions becomes almost correlated function for uncorrelated observations. But again, there is no transition to uncorrelated case. If you formally apply, use one of the parameters and send it to uncorrelated case, there is no connection. There is no limiting, no correspondence between Bickel-Herzberg. That's downside of the approach. Anyway, what we've done. So why did we do that? I just wanted to find design original idea. We had some results with Luke, and I wanted to justify why did we have this kind of integrals using experimental design point of view. That was the original idea. Of course, it developed. I mean, there were many long discussions after that, but the original integral appeared in my paper with Luke. So, but there was no connection to design. Anyway, what we suggested to do, we suggest to do the same as Bickel-Herzberg, but also change sigma square. So change sigma square, and we can get anything we want. So we increase sigma square. So instead of now not correlation function, of course, but covariance function. Now it can go to anything we want. It can go, for example, to say generalized correlation function, to some function with singular kernel. So now we get functions like that. So and now we have connection with the uncorrelated case, because in the limit we get uncorrelated observations in our expression. So basically, Saxel-Wisecki, they only consider derivative at 0 or double derivative. Bickel-Herzberg, they extended interval. We don't have to extend interval. We can stay on interval on 0 interval 1. But our covariance function tends to anything we want. If it doesn't, if value at 0, sigma n squared doesn't tend to infinity, then we're still Bickel-Herzberg type, still more flexible. But if it is tends to infinity, then we have singular kernels. Okay. So we have singular kernels. We have the same expression for covariance matrix, so-called covariance matrixes. Okay, it's limiting whatever. Another constant sigma square, which is general constant, but there is another sigma n square. So sigma n square is sigma square multiplied by n power alpha, and we're able to get all the same, except now we can have singular kernels in our asymptotics. So K, our kernel now, UV is either standard correlation kernel or single kernel. But somehow, from analytic point of view, single kernels are nicer than non-singular. Why? Just because they don't allow discrete designs. Discrete designs is disaster because there are too many of them and too many points, and you don't know how to optimize because you need to follow what Slava Melas did and or something like that. But here it's disallowed because the variance becomes infinity straight away. So if you look at that, if you have mass at one point, then you have the same point in the sum, and then the variance is infinity, so it's disallowed. So it's only densities, and in a way it's much easier optimization problem. Then we can prove optimality theorem in a similar way as we do it for non-correlated case. Just expressions are okay, slightly longer. I'll do that just for d-optimality. All these derivatives, just many derivatives. So what is the d-optimality? For d-optimality, we have almost the same theorem as for d-optimality for uncorrelated case. The same function d, but instead of m, number of parameters, we have some function which degenerates to m anyway if we tend to uncorrelated observations. That these both functions, integrals m, and everything is nice and easy for d-optimality, except, or for some of the criteria as well, except one thing, except we still haven't proved convexity. So, there was a guy called Ben Torsney. There is a guy, okay, sorry, who always did everything before we tried to do, and he discussed all these optimality theorems, but for standard cases for non-convex optimality criteria, and he made some nice remarks how it's used. But okay, so optimality theorems become not necessarily insufficient, but just necessary conditions. Okay, I'll carry on. Then how to prove what is optimal, what is non-optimal, what is okay? Can you get around this convexity? Come back to simple model and consider our variance, asymptotic variance. Now the question is it okay? There are so many experts now on positive definite functions, but is this function positive definite? The answer is no, because it looks like positive definite, but it's not. It's a limit of positive definite functions, but it doesn't help to prove theorems because there is no Bochner-Hintschen theorem, no nothing, because it's singular kernel, and you cannot take you cannot use this criterion because on the diagonal of your matrix there will always be infinities. When you take points with t1, ti minus tj. This is a matrix you have to consider. You can't because at 0 you have infinity. So nothing works. Nothing standard works here. You have to use some other thing. And Bochner-Hintschen theorem doesn't work because transformation representation does work, but the integral, the function is not integrable when you represent through this whatever function p, because p of 0 is is not 1, is infinity. So a function is not integrable, and you cannot change integrals when you want to prove the convexity, because the integrals are not absolutely convergent. In the proof of Noether, which I quoted, so you cannot do this. However, there are some other tools which help to prove, in some cases, convexity and even strict convexity of this criterion. For example, the most famous, That's where it all started. This logarithmic potential is this minus log of absolute value of u. Okay, it tends to infinity, but not very fast. There are many other cases where it appears in the theory of polynomials and the theory, and there are big books. They call it logarithmic potential theory and some other things. So this integral, which is this integral, is one of the basic, the key things there. So they try to generalize this condition to different sets, to different external forces, and God knows what. But this is the starting point. But to prove this result using this logarithmic potential theory, it takes, I don't know, several pages. So we had this integral with Luke some time ago. I wanted to prove that just to compute this constant, to prove that it's a constant for arcsine density. It took us several months. We had some help as well. Then this is our condition for optimality, necessary condition for optimality from our optimality theorem, which I just formulated in the matrix case, in the big case, but this small case. Now the question is, so this is necessary condition, but is there any other constant which density which satisfies this? So that's in a way much more difficult question. So uniqueness, it's an analog of strict optimality. We cannot prove strict convexity, but we can ask if there is any other density or measure which satisfies this condition, and the answer is not. But to prove it, okay, you can refer to some results of this logarithmic potential theorem, or you can prove it directly, which takes some pages as well. I'll come back there. So what is the problem here? Okay, we can. That's now the bigger model with f, theta multiplied by f. Generalization of that result. So again, our optimality condition from that equivalence theorem gives us necessarily insufficient condition this time. Okay, necessary condition first, that xi is optimal measure if this relation holds for all x in our interval. Okay, so people who know who can see these formulas, they immediately see that this is basically eigenvalue, eigenvector, eigenmeasure thing. But the question here is different. For example, if we talk about uniqueness of eigenmeasure, we talk about what? We talk about this f, because this is an eigenvector or eigenfunction. But for us, it's different. For us, f is given, I is given, but we're talking about uniqueness of xi, which is totally different question than uniqueness of eigenfunction, and there is no machinery in all these sciences to prove it, because in each particular case it's a different problem. It's a different analytical problem, how to prove uniqueness of this density, say in a particular case of logarithmic potential, uniqueness of the arcsine density for, say, any Chebyshev polynomial. So after some experience, you can recognize, and you can believe, or you can find, or it's not easy to find in literature, but you can check that Chebyshev polynomial, for Chebyshev polynomials, this is always true, and for arcsine density. But how to prove that? How to prove that there is no other a measure for which this is true. This is totally different problem. So that's the main analytical issue here. Okay, get back. So for this logarithmic potential, we have arcsine. For this Newtonian type, but it's one-dimensional, of course, potential, this power function, which is also, because alpha is between 0 and 1, it also tends to, it's also infinity at 0. We have beta distribution, which is called generalized arcsine distribution. For constant, again, the problem, okay, the one-way problem is not that bad. So with the help of Maple and Abramowitz and Stegan and some other things, you can prove constancy. But how to prove that this is the only density which satisfies this constancy condition? It's in a way much harder problem, and there are some other people help. And the technique is totally different. Apparently, the technique used for logarithmic potential, because there are all these very, very big books, like, I don't know, 700 pages only on logarithmic potential, but they don't know any, they say nothing about other potentials, and the technique is apparently totally different. And but there are some ways for at least for this case, to prove this uniqueness. Just to summarize, because some people who like Thales entropy, they will like this. So these two results can be summarized in one formula, because this one looks like Thales entropy. And this generalized beta distribution, including arcsine, it maximizes this double integral of this H function. So it's kind of a correlated version of Thales entropy. Now, come back to this one. For arcsine case is still different from beta case, and logarithmic potential is still easier and more tractable, because for logarithmic potential we can generalize results on uniqueness of the measure which satisfies our optimality conditions, which means that our design is unique, which there is only one design which satisfies our optimality conditions, and therefore we don't need any convexity, anything, because there is only one measure which satisfies the conditions. But we only can check the constancy condition for beta density in Gegenbauer polynomials, because Gegenbauer polynomials associated with this weight function. So it's only one way, so far at least. There's absolutely not clear how to go the other way. We went the other way for constant, but it was already technically totally different from, well, but we didn't go the other way, uniqueness for. Then, okay, some examples. Optimal design. Basically, what I said about all these Chebyshev polynomials and logarithmic potential and uniqueness, etc., implies that arcsine design is the optimal and some other optimal for polynomial regression because of this uniqueness and stuff. There are some pictures when design is optimal, when design is not optimal. There are lots of numerical pictures which don't mean much, of course. Okay, slightly earlier than planned, because there was no interruption from the back, because they promised but they didn't deliver. The theory is built, but lots of interesting problems remain. Okay. Thank you very much.
This interesting talk. Well, if you have questions, it's time to ask them.
Anatoly, thank you for a very nice talk. You probably know what I will ask. Why not use a weighted least squares? We are using for correlated observation least squares.
Because I cannot do anything for weighted least squares because they're too difficult for me. Yeah, because I don't know how to compute asymptotic covariance matrix, and that's it. I'm dead. There is no asymptotic covariance matrix. There is no asymptotic covariance.
But have you ever considered, at least for example, because you're building optimal designs for a potentially very poor estimator? Yes?
No. What I proved is that
Sometimes it's good.
it's wonderful. Yes.
But have you ever tried on simple cases or simulations?
Yes. Of course.
I mean, what is the balance of improving the design but going?
No. But it's all. There is some words there, because, of course, even if I build optimal design for my bad estimate, I can still use good estimator. It will still be better. Yes,
But
no?
It will be better, but
Of course.
it will be worse than the
It will be still worse than optimal design for the good estimate, of course. But then you use your, whatever, with Passman algo.
Yes, exactly.
Of course.
Use that.
Well,
Compare
hold
it.
on, I'm not doing magic here, except for pressing buttons, but anyway, wait. Of course it will be. I mean, the best estimate and best design is better than best design for bad estimator. No. Best design constructed for bad estimator, but then still applied to good estimator. Of course, it's better. But, and the worst is best design and good estimator. Of course, what I'm saying is the worst in this hierarchy. But it's nice mathematical problem. So, at least, okay, it has consistency because there is no consistency between Sachs-Silversek and non-correlated case. And I think there is no correlation in Sachs-Silversek case. There is no, they talk about correlation function, but there is no correlation function. The correlation function kind of disappears in Bickel-Herzberg as well, because asymptotically it's just 0,1 because if you
let us do the following. Let's fix some examples and then compete.
I'm not competing with you. No, it's totally unfair competition because we are competing on different grounds. Because you want better design, and I want more formulas or something.
Look.
So I have maybe a rather naive question about the model. For me, if you assume a model, is that you assume some truth, and when you estimate the parameters, it's like if you were trying to find the truth. So in this sense, I can understand the model by Sachs and Ebisacker, or the model by Bickel and Herzberg. But I cannot understand yours because you're changing the model when you observe more.
No.
Yes,
No, it's opposite. It's opposite.
Because
No.
square is changing.
No. It's totally opposite. Because when Sachs-Silversek is only derivative, okay. Bickel and Herzberg, at the limiting case, if they don't extend interval, they always have only. No, you don't. No, because they have no consistency between independent cases.
In one case, you assume some statistical process, yes, and you observe more and more in the interval. So this is clear for me. So I can understand so what's going on. The model is not changing, and I'm observing more and more in the same interval. In the other case, I have a statistical process, and I observe outside this interval and further outside the interval. So I can also understand in the sense that the model of the statistical process is not changing. But in your case, you have an interval and you change the model because you change the variance of the norm.
Okay, I understood the question. I'm not arguing about Sachs-Silversek, it's too difficult. Okay, Bickel-Herzberg model, in the limit, they always have, if you don't extend interval, just keep interval the same, that it means that they change correlation function. Correlation function always becomes correlation function for independent observations, but they have no relation to independent observations anyway, because it's totally different limit. There is no consistency. What we do, we say, you take any correlation function and you approximate it with, I don't know, for example, that one. So to get this correlation function, any shape you want, take our kernel and smooth it out, and that's what we were doing in practice, and the results are basically the same. So you take kernel, logarithmic or whatever kernel you take, then smooth it with, as usual. Then you don't have infinity here, you have some correlation function. We are able to basically get any shapes here. So it's totally opposite to what you say. So we are able to imitate any correlation function on the interval, and neither of that approaches can. Did you get me? Because in the asymptotics, in Pickett-Herzberg asymptotic, you inevitably get this as a limit. In Sachs-Illusek approach, they don't have correlation functions. Okay, anyway, my claim is totally opposite to what you say. So we're able to imitate any correlation function, and they are not.
But the objective is not to imitate something. The objective is that you assume some truths, you make some experiments.
That's only mental gymnastics.
And even if you don't like the asymptotics you get, I mean, this is life. I mean,
Yeah, but this is only mental gymnastics.
If you change the model in order to get the asymptotic that you like, then I don't understand what is the model.
No, wait. What is sigma n tends to infinity? We have this new parameter. Sigma n tends to infinity. You don't have to have infinity. It's sigma n equals, I don't know, 100. Is it infinity or not infinity? It's close to infinity, right? Or 1,000, or 10, or 5. It depends on the application. You can say it's infinity, and therefore you take that any of that kernel, smooth it so that your shape is almost the same, and you get that model. So I understand your point, and you are right, but I'm also right because I'm more flexible. First, I'm in between these two approaches, and second, I'm able to imitate all these correlation functions, which they can't. They by the definition, they can't imitate anything because they don't have anything at the limit. But I do, unlike them. Okay.
Okay. Any other questions? Henry?
So my mind goes back to the paper by Bloomfield and Watson on using the Cantor-Ovich inequality to look at the difference between the blue and the least squares estimated. So in some sense, we know what the worst case is for the maximum deviation between the blue and the least squares, or the weighted least squares. So in some sense, you should, if you're going to do this competition, somebody should go and look at the worst case departure from where the least squares estimate does worst. So can you tell me where it does worst?
So the worst is when diagonal is not 1. Is it because if you take diagonal, like all this efficiency, Valeri's efficiency function and stuff, totally different in different places, then you can lose as much as you want.
Yes, I mean,
and Luke has estimated for that.
it's a kind of stiffness. I mean, it depends on the spectral rate. This depends on the spectral range of the matrix. Is one way. It's a Cantor-Ovich inequality you and I have worked on.
Yeah.
I'm surprised you haven't taken that worst case and answered
Okay, but is
Raina's question by deliberately adopting the worst case rather than just say, you know, it's okay most of the time. That's not very
okay.
good.
I didn't live that long to know that paper well. So because the paper was published when I didn't have access to good journals, and I did not look back. So
You just lived in the wrong country at the time.
Yeah, as well. But you worked with these people. You know all their results because you went to their seminars. Of course, you know that, and I don't. So okay. Yeah, I agree.
I'm not sure, Mr. Chairman, that's a rather valid argument.
Okay. Any other questions? Evarist, please.
We have made a beautiful look at the history of correlated observations, but in the meantime there was a practical stream called kriging. Can you show your approach in this context?
I suggest you ask Henry, because if I start answering this, then Henry will say that that's not valid discussion, because it's all here. It's all these random fields, and or rather that one as well. So it's all these computer design for computer experiments, and there are huge programs about that.
Actually, I just make a quick comment on that. There seems to be a radical difference that typically with Krieger you use smooth. You tend to use really smooth realizations, and something radically different happens when you use these Sachs-Silberstein correlations. So the design problem is really very different for Krieger. We don't like this. We don't like sample paths which are non-differentiable.
And they don't have reliable asymptotic theory.
And there is no reliable asymptotic theory, so it's still needed. Right?
Milan?
Yeah, I have a second question from myself. If you watch in the first and second model on your slide, then I think so. You have a reasonable Gaussian process. Then you can do the similar thing as you do. So searching for invariational calculus and getting a potential, but not with respect to the Lebesgue measure, but take a Brownian motion measures related, and
No,
then
Radoslav is doing that.
yes, but nobody did.
And
So, but
then-
you will get then the least. You can do the weighted least squares, and you will see what is your solution.
So
I mean, just do the variation
yeah,
calculus.
just wait for after the break. He will talk about that. I guess. I don't know. Where is he? Are you going to talk about that?
Well, we'll see.
So, I cannot compete with Radoslav. He's young and clever, and if I start competing with all young and clever people,
It's about the Wiener process covariance structure, so perhaps that will answer your question or your remark.
No, it's not my question. I think that he should do that because then we
I'm not completely sure. I can transform these questions to the Wiener process covariance function, but only for very special class of covariance functions, the product covariance functions, and these are that would be new. I don't have a theory to transform these questions to the Wiener case.
So this is the work for Anatoly.
not a single idea. Yeah, it's probably important, but without Radoslav, I cannot even try to answer.
Okay.
Attempt to answer.
I think that after such a lively discussion, it's a perfect time for a coffee break.